Welcome to Basic Statistics for Manufacturing, a short, distinctive co-curricular micro-credential course. This course, along with other high-impact experiences like it, are an opportunity for you to intentionally personalize your education, to build on the foundation of your academic program, and to accelerate your personal and professional experience. When you complete this course, you will have a distinctive employer-valued credential to add to your personal portfolio, a validation of your knowledge in manufacturing statistics. The three primary outcomes of this course will enable you to explain basic statistics and probability principles, to apply statistical methods to manufacturing problems, and to analyze and interpret results to make data-driven decisions. There will be other intermediate outcomes as we go through the various modules of this course, but these are the core objectives. Being able to explain basic principles ensures our understanding, which will be tested along the way with brief knowledge checks. But we don't want to just have knowledge without application, so we'll seek to introduce every topic with a relevant manufacturing problem or case study. Now, perhaps the single most important word in our outcomes is the last one, decisions. We'll always try to keep our focus on data-driven decision-making as our primary purpose. You can think of this course as Statistics 101, an introductory treatment of stats with an emphasis on manufacturing. A foundational concept is that statistics are tools to help us make confident decisions, especially when we have limited information. The types of decisions impacted are broad. Decisions might involve operations, or budgets, or planning, or we might need to make a decision about process control, or quality assurance, or production timelines, or any other range of problems we might face, whether in manufacturing environment or elsewhere. Fundamentally, statistics is a discipline that involves analysis of data, its collection, organization, and presentation. We use statistics to transform raw data into meaningful information, which can be interpreted for intelligent decision-making. A statistic itself is a quantity or metric that is computed from values, typically from a sample of data. The statistic may describe an important quality of the data, such as its range, or level of variation, or central tendency. We also use statistics formally in evaluation of critical thresholds for hypothesis testing, which is a systematic way of evaluating our belief about a topic or how significant or insignificant a result is. Averages and means are common statistics that most people are aware of. They describe data central tendencies. But there are other similar statistics such as mode and median that might be used depending on the specific context and use. The count of something is even a simple but meaningful statistic used in many basic industry applications. Statistics and probability naturally relate. Probability topics concern numerical descriptions of how likely events are to occur. Sometimes the term probability is used more loosely, though, perhaps to refer to the degree of belief that an event will occur, or even sometimes as a metric. More formally, the probability of an event is a number between 0 and 1 that indicates how likely an event is to occur, where 0 indicates impossibility and 1 indicates certainty. Higher probability, of course, means an event is more likely to occur. Probability relates to the frequency distribution of data, often depicted in a histogram chart, like the bar chart pictured, or described by a probability density function, or PDF, which we'll use quite a bit in our analysis of data. Because this micro-credential is focused on helping you gain industry-relevant knowledge, we'll keep the topics focused on manufacturing. In particular, we aim to deal only with practical measurement applications of basic stats useful for decision-making in industry. We'll do our best to employ only commonly accepted industry terminology and to avoid theoretical topics, though we of course will use mathematical formulas, including calculus, to define some fundamental statistics. The intended audience of this course is engineering undergraduates. Our course structure generally includes an introduction, a case study, discussion of central tendency and dispersion statistics, and measurement-focused statistics with applications such as dimensional measurements. We'll also cover regression, probability, and hypothesis testing. And practical example problems and knowledge checks will occur throughout. Note that this course outline is distinct from a general undergraduate statistics course that follows the table of contents of a traditional textbook. We value such courses and encourage students to take a semester-long statistics course if possible. And we can't possibly cover every topic in a short co-curricular course, so there will be some gaps in coverage. Hopefully, this course will provide broad exposure to common topics and motivate the interested student to understand why the application of statistics in the real world can be so beneficial. Speaking of the real world, before diving into statistics, it's important to discuss trends in industry, more specifically the manufacturing industry. Hopefully, this will help establish the intrinsic value of why this course, why it matters. We'll start with a recent report titled Future of Manufacturing: New Workflows, Roles, and Skills to Achieve Industry 4.0 Business Outcomes by Christina Batelli as part of an ASME Autodesk collaboration. A link to this paper is provided on the course website. According to the report, the manufacturing industry faces a confluence of changes that will significantly transform the roles, skills, and workflows of engineers over the next decade. These changes are driven primarily by pressures on businesses to achieve outcomes. Some of those outcomes are related to improved computer-aided design, computer-aided manufacturing, productivity, output, and profitability, reduced cost, competitiveness, and sustainability. In part, success depends on developing new manufacturing education opportunities to effectively train the necessary Industry 4.0 technologies and skills. Some of the important skill categories highlighted by the ASME Autodesk report include technical or hard skills, such as artificial intelligence, machine learning, programming, data analysis, and visualization. Soft skills, such as collaboration, communication, and problem solving. And more interdisciplinary skills, like systems engineering, automation, sustainability, supply chain management, and product lifecycle management. There were several examples of emerging industry technologies mentioned in this report. Some include design for manufacturing, operations technology infrastructure. Also mentioned was artificial intelligence and machine learning with technologies like generative design, and cloud-based software platforms like integrated CAD/CAM. Also mentioned was project lifecycle management and manufacturing execution systems and their BI tools. And technologies include enterprise data management systems for collaborative data analysis. Large volumes of operational data will become more and more available, especially with the adoption of the Internet of Things and other Industry 4.0 technologies. Engineers will need the tools and skills to extract meaningful information and insights from data. In a survey of 171 mechanical and manufacturing engineers, 69% of the respondents indicated that future engineers will need data analysis and visualization skills in their toolbox of core skills. Some programming, particularly knowledge of low-code and no-code methodologies, is also going to be needed to identify areas to optimize and automate. So, in order to drive performance, profitability, and production, engineers in the manufacturing industry will increasingly rely on massive streams of data to inform their decisions. So basic fluency of how to analyze, interpret, and transform data with statistics is going to be critical. Industry 4.0, also known as the Fourth Industrial Revolution, is a new era of manufacturing that's characterized by cyber-physical systems, the Internet of Things, and big data analytics. These technologies are enabling manufacturers to connect machines, devices, and people in real time, and that's leading to more efficient and flexible production processes. Cyber-physical systems are physical devices that are embedded with sensors, software, and network connectivity. This allows them to collect data, communicate with other devices, and make decisions without human intervention. The Internet of Things refers to the network of physical devices that are connected to the Internet. These IoT devices can collect and share data about their environment, which can be used to improve efficiency, productivity, and decision making. And big data analytics generally refers to the use of large data sets to identify trends, patterns, and relationships. This data can be used to improve production design, manufacturing process, and customer service. Sometimes we call this data science or data mining. Industry 4.0 is still in its early stages, but it has the potential to revolutionize manufacturing. By embracing the new Industry 4.0 technologies, manufacturers have significant opportunities to improve operations, reduce costs, and create new products and services. At the highest level, manufacturing statistics are used to track performance of manufacturing systems. Statistics help decision makers set goals, monitor progress towards goals, and drive improvements. Some common manufacturing statistics are output, backlog, throughput, inventory, yield, waste, cost, and cycle time. Cycle time is sometimes called span. Note that some key statistics like output, backlog, throughput, and inventory simply require count. The simplest statistic of all, the total number of items. For example, inventory is the amount of items on hand, and backlog is the number of orders not yet filled. A high backlog might be a good indicator of demand, but it also might be a sign of a process bottleneck or inefficiency. Other statistics like yield and waste use percentage, which is just a simple way of normalizing count relative to a total or reference value. Waste materials and products, especially those that have been rejected by quality assurance and scrapped, are other signs of inefficiency in areas targeted for improvement. Of course, time equals money. Total cost and cycle time are also key statistics that require very little math or theory to understand. By tracking manufacturing statistics, Industry 4.0 ready manufacturers can make better choices about how to allocate resources, set prices, and improve their operations. By identifying areas where improvement is needed, manufacturers can make their operations more efficient and reduce cost. By tracking quality metrics, manufacturers can identify and address problems early on, preventing them from causing costly defects. And by meeting customer expectations for quality, delivery, and price, manufacturers can improve customer satisfaction and loyalty. The overall main benefits of using manufacturing statistics are the key drivers for why a course on basic statistics is important. Manufacturing statistics allow increased efficiency, quality, customer satisfaction, profitability, and ultimately improved decision making. That completes the introduction to basic manufacturing statistics. You should attempt to complete a brief knowledge check before moving on to the next module, a manufacturing statistics case study.